I think, but it's going to be a bit of a sort of a medley of things. And spoiler alert, and Michael has already spotted this, of course they have nothing much to do with each other than I'm interested in both. Well, you could say they both have carbon. So I sometimes sell it as working on the shallow and the deep end of the carbon cycle, you know, for if that sometimes gets traction. But it's also what it also connects is the methods I'm using. So I kind of use methods in the one field and then translate methods that maybe are a bit more uncommonly used in geochemistry, petrology from biology and mineralogy into that area, and that sometimes actually yields quite interesting insights that you wouldn't probably have if one stuck to the rules and keeps thinking inside that box that one is so comfortable in. And why doesn't this now? That works anyway. So it's going to run through two topics here. I really have more topics that I do or used to do research on. Here I'm trying to actually quarantine 1 day per week, so you might all notice that my Fridays are not really bookable because I either have to write up the papers that I should have written up last year, or I will actually do stuff in the lab in the future. So there's that, and part of what I do on Fridays is part of all of these things. So we're going to go through these calcifying critters in the ocean, which is where I started from. And the thing and why they are important is of course quite obvious in this school, because there are actually important archives of past environmental conditions. Like trees, many of those marine calcifiers grow in increments. This here is a polished section of a bivalve shell, which has been dyed, stained, and you can actually see yearly increments that are sort of visible here. Corals do the same thing, and this here is an exceptionally long record from a freshwater bivalve in Sweden. Corals give you a lot longer records, of course, but bivalves have the advantage that they grow mostly in areas that are temperate in climate or even cold climate, whereas corals, we have cold water corals, but the bulk of them is in the tropics. So that's just another archive. They're all really difficult to read in some respects, some more than others, because while they are consisting of calcium carbonate, calcite crystal here, you can see from this coccolith here, the shape is nowhere near what it should be for a geological calcite. So they have they're far away from equilibrium, what we expect in the geological record. And the reason for this is that all these minerals are formed by organisms, which basically means that every single ion has to pass through a cell, through a living cell. There are exceptions to that rule, but the most important thing is there's metabolic control over shape and composition of this mineral, which also means that this is not solution chemistry. For the longest time, people have tried to explain these things by supersaturation and then sort of, you know, precipitation of calcite because from supersaturation solution. This is not what that is. There's active transport involved through cells, through cell membranes, along cell membranes, using enzymes and all sorts of proteins connected with this. And this is basically a completely new area of research where we know very little about, because it is situated at the edge, at the interface between mineralogy, chemistry, geology, and biology. And so you actually have to work together with cell biologists to actually make progress in this area. And not many are interested in that kind of topic. So what you get is crystals or grains that are quite different from the geological counterpart, both in composition and in shape. And what you also get is that these biominerals always contain a certain fraction of organics as a coating, but also within the crystal. And while they diffract with X-ray diffraction, people have looked at this, and for the longest time they thought they're single crystals because they diffract like a single crystal. What we know today is that there are multiple highly aligned twins. So they're poly twins, little crystals that diffract as a single one. And because they're mixed in between organics and inorganics, they have very different properties to their geological counterparts. So why bother, would one ask? They're beautiful, of course, but why would we sow our champignons, or I don't know, whatever is, why is this actually relevant? And they're relevant because we need to quantify. I mean, the real reason to study those is their archives for paleo environments. And if we want to quantify things, we need to understand how these elements are actually incorporated there. Currently, most of this is empirical, which works for many species. It works quite well in the coral area, I think. It does not work at all with the bivalve shells, and we don't know why. It might be connected with, it was stuff that was lumped together in the past as vital effects, but this is really a bucket term, and we don't even know what parameters play into this vital effect term. So it's also important to evaluate the resilience of the marine calcifiers. It's important for the pearl industry. It's important for the aquaculture industry with the current progressing climate change. And it's also interesting for engineering because these shell strength is a function of structure plus composition. We don't know this at small scales for any of those species, and they actually form the basis for new materials. People trying to create new materials with emerging properties, which are properties that every single piece of that new material doesn't have, but the combination of it has new properties. That's really what we use that for, or what engineering uses that for. And of course, uptake of elements in isotopes and fractionation of these things is influenced by the mineralogy as such, and therefore we have to understand, eventually we have to understand how that actually works. And the basis of this is, which I get to later, is that all of these, or most of these, as we know now, most of these marine calcifiers crystallize their shells through a non-classical crystallization pathway. And that involves different phases. They transition through several phases that are metastable until they actually reach the stable calcite phase. And that all influences the chemical composition of those. So the way I started to get into this, I talked a little bit at lunch about this, is that I ended up at a department that had a gemology group. Gemology is the study of gemstones. Pearls are gemstones, bio gemstones. And we actually had people from the trade coming to us saying, we've got these pearls here that, I mean, maybe you can just see, they have white spots, they couldn't sell them, they were blemishes, and they didn't know what happened. So we thought, okay, like, why don't we have a look, how hard can this be? And we found that while the pearl is aragonite, these white spots here consist of butterite, which is a polymorph of aragonite with a different crystal structure. At that point in time, the crystal structure was not known. And that just influences the luster of the pearl, so they couldn't sell it. So one thing led to the next, and in the end, I actually had a fully fledged research project, which then got me a future fellowship, and here I am, still working on these things. So in terms of mother of pearl, we thought, okay, what else could you possibly learn? I've put this quote up here from a Shakespeare work, 16th century, already people, and much earlier, we know that people were interested in mother of pearl. So I thought we are not going to find anything that would be new. Little did we know that we actually then produced some new knowledge. Mother of pearl, if you break it, look at it under the SEM, they're tablets like these. I said they have up to about 4% organics and a bit of water. So if going closer, you can just about see that the aragonite tablets here have this coating of organics around them. Schematically, doing it like this here, so you have like hexagonal or pseudo-hexagonal aragonite tablets that come in layers, and each of these layers is formed by organic matrix that people thought was chitin. So we found it's actually not chitin, it's actually silk-like protein, which wasn't known. And also the other thing is it's not just in between these layers of aragonite, it's also within the tablets. This image here is a tomogram taken with the transmission electron microscope, which shows you all these little, so the scale here is 20 nanometers, and all the blue things. So the aragonite in this image is rendered transparent. and all the blue blobs here are organic matrix, as we call it, because we don't still know what molecules that make up. But you can see they're all dispersed within this aragonite tablet. And that's quite important for this, for the mechanical properties of this, of these aragonite tablets. But it's also what came out through works from other people is that these organic molecules actually guide the crystallization, and they actually shape the form of the crystal while it's growing, or of the grain while it's growing, and they also align the pieces so that they will become twins. How exactly that forms and which groups are actually mechanistically involved, we don't know yet, but this is the job of these organics. But then, as I said, it's also because in terms of new materials, the emerging properties of mother of pearl are quite interesting, because the one thing they have is they completely outperform calcite or aragonite as we know it geologically. So they have, mother of pearl has 1,000-fold higher mechanical strength than geological aragonite, and it has a hierarchical structure, which I'll get to in a moment, and it has these organic layers. And we had, we were then involved, actually with my postdoc, then PhD student Laura Otter, who worked with a group of material scientists doing nano indentation in the transmission electron microscope, which is schematically shown here. And it was, this is the load change here, and what you can perhaps see is that the pressure increases, and we went up to 1.2 gigapascal before the tablet breaks, but up to 1.2 we can see complete recovery. So meaning that they were smashed together, but then if you release the pressure before you come to the break point, you get a full recovery. It all looks like before. And the reason why this works, and that of course would not work with normal geological aragonite, and the reason why that works is because you have these many little organic inclusions here who change their shape when you press. You can see here you have 3 blobs, there we only have 2 blobs, but then when you release you go back to 3 blobs. That's one reason. And the other reason is you have these soft materials, this interlamellar organic sheet between the tablets of aragonite, and while the aragonite behave like a monolith, these sheets in between stop the crack propagation. So whatever happens to the thing, it's the combination out of this organic and inorganic material that actually makes it so high performing. And so this group was really interested. That's a group of physicists in Minnesota who work on material sciences and are actually designing new materials based on, or hoping to design new materials based on these natural things. So we were more interested to actually figure out how does the shell do it, how does the bivalve actually do it. We're still not there, but in terms of understanding better what that material is, we went to more SEM and atomic force microscopy, and you can see that it actually, if you look at a single mother of pearl tablet, it consists of little granules. Each of these granules shows up here. This would be the outline of the aragonite tablet here. And each of these granules is in fact, we found, coated with an organic coating. Whether this is a proper cell membrane or whether this is just a lipid coating, we don't know. But you can see in the TEM, in the transmission electron microscope, if you do a calcium map, you can see, okay, here we have all the calcium carbonate around here, not so much here. But in this area where you can actually clearly see these granules, you can also see enriched carbon around these granules, which where there is no calcium, but you have carbon around here, meaning that this is in fact a membrane. What we also found is the crystallinity is variable in one of these aragonite tablets. So we have areas in the tablets that are just not crystalline, they're amorphous, and other areas that are properly crystallized aragonite. We found that out with Raman spectroscopy. You can do tests. We found areas that are amorphous, because you wanted to know, is that really amorphous calcium carbonate, or is that maybe just organics which are just often amorphous? So we found areas in pearls and shells that were amorphous, judging from the Raman signal. Normally you would get really peaky patterns. With amorphous material, you only get flat curves. There was a little peak here, which could have been the calcium carbonate, the carbonate peak. And to test whether it really we are measuring organics or mineral, we just left the laser on for a while. And we found then later on, when we, after 10-15 minutes, when we took a new spectra on the same point, we found that in the meantime, the whole show had crystallized more. So that is really a sort of a very clear evidence that we are not measuring organics, we're actually measuring calcium carbonate, and it is amorphous in the shells. And that was quite a surprise, and we were the first to show this. And then the question is, why do you even have amorphous area in the shell? Because it's the way we think of crystallization, it's an ion by ion building of a crystal. This is what we're taught at undergraduate level, but this is not what we see here. So to dive a little bit further into this, we used focused ion beam assisted transmission electron microscopy. I don't know how many of you have done this. We've got this here on campus in CAM. Just as a bit of an explanation, what you do is you use the SEM to cut an electron transparent foil out of a very defined area of your sample. Electron transparent foil means the foil is about 150 nanometers in thickness. In this case, we did this with one of the shells. This is the section of the shell. This is the aragonite, the nacre part of it. So we found an area of interest here, close to the outer layer on the shell, which is organic. And we then sort of, this is here from a publication of the guys where I did this with. So basically you have a gallium ion beam that digs a hole. These crosses are here to correct for the drift in the SEM while you cut, because otherwise you're never getting that foil out of that ditch here. And then you basically cut a ditch in front and behind, and you're left with a little foil here that you then can cut out and lift out, and you can use this for analysis. The foil often is covered with a platinum strip here to protect the area of interest, and that's the platinum strip you will see in the next slide, because then you can actually take this foil, you can do all sorts of things. You can do EBSD with it, you can do TEM with it, you can put it in the SEM, you can put it in the microscope, you can put it in the shrimp if you wanted to. We chose to put it into the transmission electron microscope. So this is the foil we took out from here. This is the outer organic layer of the shell. This is the platinum cover. And you can see from the scale bar how small this foil is. That's about 15 microns by about 10 microns or so, 150 nanometers in thickness in some areas. So while we were cutting, it was bending a little bit. Therefore, we ended up with a little bit of a crack here, and with some areas that are a bit thicker than other areas. That's why it's a little bit more gray. But nevertheless, we have a piece of the shell here, which is calcium carbonate. You can probably just see the granular texture. It's a bit closer here. This is then our area where we focused on, and we actually could use that funny crack that happened as an artifact, really, to zoom in on an area where we were really interested in. So, and this is then this here. So you have this granular structure that we've seen in the SEM images. This is the crack right here. On the left side is what is not so interesting for us, is that outer layer of the shell. And we're zooming in into this little area here where we have several of these granules sitting. So, and this is then this here. So you can see you've got these granules. This is the crack. There are some sort of strings here, which are the organics connecting all these granules together. We made sure that we're actually really looking at calcium carbonate. That's of course a prerequisite, otherwise you don't know what you're getting. So we took a dark field image, which shows you which areas are crystalline and which ones are amorphous. So everything that lights up in white here is crystalline. These areas, however, do not light up. So there are, in fact, amorphous calcium carbonate. There are calcium carbonate as shown from the calcium map, which gives you a very clear signal for calcium carbonate. And the carbon map shows you it's not enriched in carbon, so we're really looking at calcium carbonate. And what we did then is we did electron diffraction across one of these granules to see if it's actually crystalline or not. So we chose this one here, which showed up as amorphous, and I've indicated the traverse that we did here. So at the rim position, we got a diffractogram which shows us it is actually amorphous mostly. We have an area here where we did find a little bit of crystallinity, but you know, I mean, a little bit is fine. Still, the majority is amorphous. Then we moved further inside, and the further we went inside, the more dots we found on the diffractogram, meaning that we're getting more and more crystalline things. So we could actually show that this is in fact an artifact. We had actually started to crystallize it under the electron beam. And we did this, you have to be really careful to not create artifacts like this. It was unavoidable, but we documented every step, and you can actually take precautions to be sure if you're creating artifacts or not. And even if we created an artifact, that just means it was all amorphous before. And I'm just pointing this out because in the transmission electron microscopy literature, there's actually a lot of artifacts. And it's one of the main jobs publishing in that area is to actually have a foolproof protocol to check and recheck yourself if you're actually going down a rabbit hole and you're actually looking at artifacts. So that was a big learning experience in that project, and it wasn't our first electron diffractogram that we produced there. Anyway, so what we showed is, and that was really the new thing about it, that mother of pearl actually consists of these organic coated granules as small as building blocks in every one of these aragonite tablets. And that the shells in fact crystallize from an amorphous phase, and that's why they still contain patches of amorphous calcium carbonate, or ACC. And this was at the time where several groups around the world started looking at these marine calcifiers. There's a famous group at the Weizmann who looks at sea urchin embryos and these things, and they all kind of independently from each other came up with the same observations. And that in fact observations like these on marine calcifiers actually led to a huge paradigm shift in chemistry that is now called that went away from the classical crystallization, ion by ion, building up a whole crystal, and went to something that is called a non-classical crystallization theory, where, and you see that's been published in Science, then where people recognize that there are many pathways from a solute, from ions, atoms, and molecules to the crystal that do not just involve the classical way, monomer by monomer crystal growth, but actually talk about different ways to build a crystal with through particle attachment. And the way that the shells are crystallizing and are built is just one of those pathways that does not use ion by ion, but actually uses particle attachment. And that was brand new at the time, and I mean it's really quite, I found that quite exciting to see how these observations in our realm on marine calcifiers actually led to such a huge paradigm shift on concerning theories that have been there in textbooks for hundreds of years. So that was really interesting to see. That also means that because we model in geochemistry, when we model systems, we come from this equilibrium crystallization theory. We have the solute, and then we start crystallizing classically monomer by monomer, and that we use that to calculate partition coefficients. And looking at this and seeing and accepting that shells actually grow differently just tells us that this is not the right model to explain what happens in the calcification in the marine realm when organisms involved. So that was the big finding, and that was also something that I wanted to take further. And then I had a discovery grant with Steve Eggins together, where we started looking at foraminifera, and we basically found the same thing. Oscar Branson was involved as well, and that's actually one of Oscar's images that you probably all know quite well. And we found the very same thing for most of the foraminifera that we looked at, that they actually start out with amorphous calcium carbonate and then go through metastable intermediate phases until they finally turn into calcite. How fast that happens, we don't know yet. We know everything in the fossil space is calcite, but everything in the alive space is actually ACC first, and you still find patches when you look at the foraminifera shells with the right soft beam protocols. The impact that has on the composition, I have here just for as an example for mollusk shells, you can see we have aragonite and we have amorphous calcium carbonate, ACC in red, but you can see compositions can be quite different, and this intermediate phase vaterite can yet be different again, and we don't actually have a good handle on what rules this and how can we best model this and bring this into our sort of general model for the paleoclimate archives. And similarly for the foraminifera, to explain the calcium isotopes, we think there is probably a double fractionation effect at work, perhaps here, that could explain this fractionation along with all the metastable phases. It's hard to study these because, as the word says, they are metastable. So it's really difficult to actually get a grasp around that system and how we best study this. So that's as far as we were there. So in conclusion, for this part, we were lucky enough to be the first, and it's just really often luck and timing and asking the right questions to prove that the mollusk and the foraminiferas form their shells from amorphous calcium carbonate and only later crystallize, which leaves behind some patches of stuff that never made it, that was stabilized by the organics perhaps and prevented from crystallizing. That of course debunks the long-held textbook knowledge, and we have to do more work in this area. We contributed to this fundamental paradigm change, which was really exciting to see that happen. But it also shows problems. It shows that our theoretical basis for reading these environmental paleo records is actually invalid. And I've got my discovery grant funded this year to actually start working on trying to see how far away are we from valid. Can we approximate this? How do we best approximate this? Is this the only parameter that falls under vital effects? And I think that there's another lifetime of work there if I'm not careful. Right, so this is that part, which gives a little bit of an overview. I should probably say my postdoc Laura, who you probably know, is working in that biomineral space, and we have started talking with Michael of how to get this aquaculture back going and getting from a terrarium to an aquarium feature in flora again. Second topic is for the hard rockers, the diamonds I work on. So some of you might have seen these beautiful pieces here. These are very large diamonds, very rare, very expensive. And now we know that these large stones have inclusions that are compatible with the derivation from the lower mantle. We don't know anything. Why can they grow so large in the lower mantle? How do they actually come in the area where the kimberlite can pick them up? But it's one of the most spectacular specimens out of this range. Diamonds are brought up by kimberlites. This is one in Canada that I went on a field trip on. Greg was on the same field trip and isn't here, but never mind. And they produced an element issue later, which also has a contribution co-authored by Greg Yaxley in it. So if anybody wants to read this, this is nice. So basically, kimberlites are holes in the ground. They come from deep in the mantle, lithosphere and asthenosphere, some of them, and they are the ones that bring the diamonds up. So I'm sure most of you are familiar with that cut through the earth. Which just explains that diamonds are often, or the classical areas of where we find diamonds, and the big diamonds are in the subcratonic lithosphere, from where these little kimberlites bring them up. I've just shown you some of them come from the lower mantle. How they get up here for the kimberlite to pick them up is still unknown. So there's still room for some PhD projects if someone wants to take that on. And you can also see that this is probably quite connected with the general geodynamics and with subduction zones as well. I have, some of you might know, I've started my scientific life out at working on these aggregates, which are the original classical host rock of diamonds. That an aggregate was the first rock where diamond was found in 1899, I think it was, but I'm not going to touch on this today. The lower ones, the best model for now, and you can see from the drawing that the model is very fuzzy yet. The best model we have for now to explain these lower Mantle diamonds is from a deep subduction area where we can derive the agents for making the diamonds and their inclusions and bringing them up. That's just one, this is one diamond on one of the eclogens that I did my PhD on. So I guess I'm drawn to the nice gemmy things. But the diamonds that I work on are a bit of a different species. They are polycrystalline diamond aggregates. They are also known under the name board or framesite, stuartite. Carbonado is one of those. I don't work on carbonado. And these polycrystalline diamond aggregates are not quite so beautiful, but that's probably also why I get access to them, which sometimes it helps. And they are actually, I think they're probably in some respects better than the normal gem diamonds. And I guess I have to say that, I guess. But because they are so graphic looking, they actually have a lot of inclusions. So we have a lot more opportunity to tell a story there than having a nice clear-cut, beautiful gemmy diamond. So there are very small crystalline, so they have crystallized sizes between 10 microns and a couple of millimeters. They're basically rocks made out of diamond. They're small, so you don't find a whole outcrop of them, but they're a couple of millimeters or centimeters in size. But the rock-forming mineral is actually diamond. And the silicates and any other inclusions are minor components of that. So that's a bit of a different concept here. And the reason why they're so small, the crystallites are so small, is because they're crystallized fast out of a highly supersaturated solution or a medium or fluid, if you wish. So they are, and that's different to the gemmy diamonds that can actually grow over millions of years, have episodes of growth and resorption, and kind of average out what affects them. These are more snapshots. They're more extreme. You find all sorts of really extreme stuff, highly heterogeneous, but they provide snapshots of a process that operates in general for all the diamonds. So we can learn about diamond formation from them, but from a different perspective, which is always valuable. And the other thing is that they are actually, not all of them, but some of them are clearly young. Diamonds are forever. We all have learned this thing from De Beers. I think that was their marketing take. But some of these are actually remobilized carbon that has formed just before kimberlite eruption. So that was another new thing about these guys. They are, I said, they are very heterogeneous. So they have the table shows you how the ranges are. So some individual samples cover most of the data set. That's possible. And they're also distinctly different from the gem diamonds or from the monocrystalline diamonds in that they have a lower carbon isotopes and they have more positive nitrogen isotopes. And just to highlight a couple of things, they give spectacular cathodoluminescence images, which is always nice. So here on the left, you've got, and that's growth zonation that we see here. So you see there's a lot has happened to this one. It has cores that are dark. They looked a bit like they were brecciated or so. Then you have light rims. And then you have this stuff here in the middle. It's all diamond, but it's all different in composition. In yellow, these are SIMS spots. So you can see that the carbon isotopes range between minus 12.3 and minus 23.5. Nitrogen is sometimes really different. It's 2,500 ppm up here. It's not measured, it's below detection limit. Detection limit is 30 ppm in this one. So you get obviously different pulses of growth in here. You've got this one over here that actually looks like a fracture. It looks like it's something broke it up and came between it. It's all diamond, but it is different fluid pulses. So that was really interesting and just highlights how heterogeneous and how fast these processes must have been. But they're probably also episodic. We don't know how much time lies in between those. but we do know that they're distinctly different. There's yet another example, quite beautiful, this one, I think. So on a nitrogen isotope versus nitrogen concentration plot, you can see that there we have two populations measured by SimSpot, and these are sort of the gray mass in between here and the light shiny ones here, so that they're quite different. As I said, different pulses, that's as far as we are with this, but we don't actually know yet how much time lies in between them, because, and part of this is because they're actually quite difficult to work with. It's diamond, you know, you've got to polish that. It's not quite so straightforward. Diamond has this hardness anisotropy. Some crystallographic areas are much harder than others because they're polycrystalline. It's a random assortment, so you always get stuck with this hardness anisotropy. So it's hard to polish. It's also hard to look at these inclusions because they're mostly black, as you saw. You can't see through, so you basically have to cut. You have to either laser cut or do. We chose to do focused ion beam cutting, and cutting a focused ion beam foil from a diamond takes about 10 hours, and you pay by the hour, so you're a bit limited by the budget. What they also have, and that's just another SEM image here, they're very porous. They have up to 30% porosity, and they're formed in the upper mantle. So obviously that wasn't air in there at the time, but it was some kind of fluid. But it just speaks to the fact that the fluid has a prominent role in the formation of these diamonds. And it's either fluid that came or it's fluid that was generated while the diamond was formed. So there's a big pore here, and all of these black little spots are actually little pores. That's just another image of a broken piece where this is a garnet, and you can just see the little diamond crystals sticking out of this mass of garnet. So it's not just the diamond that, or the pores between the diamond crystals, but it's also pores in the inclusions. So they have inclusions in the diamond crystals, but they also have mineral intergrown with these diamonds, as this garnet here. We studied mostly, I mean, you have a lot more material when you look at the stuff that's intergrown with the diamonds, because the diamonds are so small. Clearly the inclusion is even smaller, so you are very limited there. So we concentrate often on these intergrowths. And these intergrowths can be all sorts of things. Here it's a garnet. It can also be magnetite. And on the left here is a focused ion beam foil cut through one of those diamonds that had a magnetite inclusion here. And when you get a close-up of this magnetite, you can see that also the magnetite has a lot of pores, which were probably fluid filled. And sometimes one is lucky enough to still have a cavity in one of these diamonds where we can still see the fluid. So this is basically the diffraction contrasts that are oscillating under the electron beam. And I took 10 or 15 pictures and made a GIF out of this. And so you can see that this is fluid here, and there's a little bit of mineral there. And that's as far as you get with TEM to say what it is, because TEM is not exactly the method to analyze the fluid from. We also used microcomputed tomography just to show what these cavities look like. And I've got a little movie here, maybe it even works. So in this one, the diamond is rendered transparent. So you can't see the diamond. The red stuff are the pores. Some of them are connected, not all of them are connected. The purple stuff are the magnetites, so it's a large overrepresentation of magnetite in these things compared to what we find in gem diamonds. And then you can see that these magnetites have these green halos, and these are in fact what you can also see on this pip foil here. This is an alteration rim, which is a mixture of oxidized phases and some phyllosilicate, which is a late stage history of this sample, which also then highlights the problems, because unlike in gem diamonds where the inclusions are shielded by the diamond and you are sure you have pristine information, in these rocks it's intergrowth most often, and they're open to the environment, and you can actually get metasomatic effects. So you have to actually sit down and deal with each sample and figure out what is primary information and what is secondary information, and have some checks and balances around this. And just as a last little bit of highlight of these studies is, and that's really an example of where I took the methods I was using with the biominerals and used it on the diamonds. And that was not often done. And then this got us into a really nice paper, nice journal with this study, just because it was thinking a little bit outside the box. That using fit-assisted TEM analysis, again, we were cutting this foil through this one diamond, and we found in this foil, and that was really between you and me, this was really luck, you know. So we cut about 50 foils, and one of them had happened to have these beautiful inclusions here. We had one inclusion here, one inclusion there, connected with this little veinlet in this foil, which was otherwise just diamond. So this up here is just the gallium precipitate from the gallium ion beam. So that's an artifact. But the rest here is diamond, and it has these two inclusions. That's another image here of those two inclusions. And then you can perhaps just about see that this inclusion here has a rim. So we got interested with this rim, and then we used a method called TKD, which is electron backscatter diffraction on a FIB foil. So it's TKD called for transmission Kikuchi diffraction, which is just another method of EBSD, but on these FIB foils. And firstly, we could see that, okay, this large inclusion with the rim is in fact a pyrrhotite. This pyrrhotite is protogenetic because it showed deformation. The diamond was not deformed, the inclusion was deformed. You cannot deform one without the other if it had been included. So this deformation had to have happened beforehand. So this sulfide was actually not formed with the diamond, but it was randomly included by the diamond after it had already been formed. So it has a prehistory. So that was an interesting finding. And then the other finding where we were going to look at this rim, which turned out to be a reaction rim, that proved to be quite difficult because that foil was still too thick for that. So what we did then is we shipped that foil back to where it was cut, which in my case was in Potsdam in Germany. And I asked my colleague there to thin the foil so that we could actually start studying the rim. So she put that back into the machine, run the gallium ion beam over it. The effect was, and we did this kind of in real time on Zoom or on email in that case, on WhatsApp. And what then happened is that she actually lost most of this innermost part when she cut it, which is always a danger. Fortunately, we had already analyzed this, and it didn't bother us that it was lost. But the good thing is that this reaction ring was thinned to an extent that we could actually study it better. And then we got really good EBSD or TKD data on this reaction rim and found for once it is magnetite. The reaction rim was magnetite, and it was magnetite consisting out of all small nanocrystallites. We could get orientation data for these nanocrystallites, and we could also see that in this way we could see that they were actually twinned. So these were twinned little magnetites forming a reaction rim around a sulfide in a diamond. I said again, the sulfide was already there before the diamond formed. We found that there's epitaxy, so the crystallographic orientations were aligned between the sulfide and the magnetite, and between the magnetite and the diamond, which is a sort of an absolute clear sign for the fact that one grew on the other. So we had the sulfide on the rim, along the rim of the sulfide, we grew the magnetite, and the diamond actually nucleated and grew on the magnetite. So this turned out to be the first direct observation of how diamond actually nucleates and starts forming, right? So the story is therefore that we had the sulfide, there was a fluid coming along reacting with the sulfide. This is a redox reaction, and this reaction formed, reduced the fluid to diamond and oxidized the sulfide to magnetite. And those formed a reaction pair growing on top of each other. What we learned from these twinning borders here, luckily, we found that there is actually a high pressure phase that forms from magnetite above a certain pressure. And these twin boundaries are a clear sign for this, for retrogression of this phase, the post-spinel phase. And there was even a paper that described this, so that was really lucky and that calibrated for us. So this is the first ever depth determination for any diamond. And that is actually put it at the base of the lithosphere, which under that specific locality is 300 kilometers depth. So that was a very, that was a good group coming together with specific skills. Nobody could cover so that's really what interdisciplinarity makes out. Nobody has the entire knowledge. We all bring something to the table. Nobody could write the whole paper on their own, but we all worked together and came up with a really interesting finding. And of course, there's always, like in everything, there's always a bit of luck to pick the right sample, to be lucky to have that thing happen to you at the time. So in conclusion, what basically that diamond work shows is diamond formation happens episodically in the Earth mantle, no diamonds forever. Not all diamonds are old. And these polycrystalline diamond aggregates have a value in that they preserve evidence for diamond formation, like snapshots in a very extreme spectrum. And in this case, we found that there are redox reactions at the base of the lithosphere at work. Thank you very much.
So we can do questions, and I guess we have this microphone to make sure that people at the other end can actually hear. Yeah. Any questions? Sorry.
So I have a question about both topics. The first one, does the calcification of the crystallization of the organisms, does that happen while they're alive or after diagenesis?
No, that's when they're alive, when they first form the shells. That's kind of how they form their shells.
Just not sure at what stage.
Yeah. Well, it's I mean, they form the shells when they're alive, and that's when they start with the amorphous pathway. It will have to recrystallize some time later, and that is often, I mean, that's diagenesis for once, and we're currently not quite sure if that actually happens through the lifetime of the animal, because we haven't actually. It's too short a time to actually go across the shell in the case of foraminifera to see when that actually happens. You could test this looking at the innermost part and see if it's still amorphous, whereas the outermost part is still is already calcite or so, the other way around, but it's tricky.
Yeah.
There's not a lot of material to work with.
And my second question is, the pore space in the diamond, how do you know that happened at depth and not later during respiration?
Well, it was certainly filled with something, but not with diamond. I mean, the fact that you have pore space is really not typical for a rock. So there was something in there, but it is long gone, and it hasn't been refilled. So it's not water that went through and did this. In carbonados, that's sometimes what we find, that there's some phases that are sedimentary, fluoride and these things, and they are probably brought in through pore water. But in these, they come fresh out of the kimberlite, and the spaces are just empty, air filled now. But there must have been, I mean, in the mantle, there must have been other things in there, but there's no remnant of some mineral or so. So the most likely explanation would be a fluid.
How do you keep the spaces empty?
Yeah, if we have gas or fluid in there, I mean, you have to hold it apart. Yeah, that's a fair question. We don't really, it's not just empty. It's some gas in there. It needs to be pressurized. We're stuck with that microphone now.
Pass it on to whoever's next. In the meantime, I think I can be heard. So Jochen actually asked from online, what method and instruments again do you use to make the nanometer spec of pearl invisible in the aragonite tables of pearls? The resolution is spectacular. Could this also be applied to siliciclastics?
So the first step, what the first part was?
What method and instruments again do you use to make the nanometer spec visible?
Transmission electron microscopy. You can do tomography with it. It's a bit tedious, but it's a great method, and I'm sure it could be applied to whatever you would like to, as long as it uses the density contrast. So as long as there is a density contrast, that's possible. On campus, I should say, Jochen.
Oh, there you go. And the second question, have any physicists tried to theorize or simulate this novel crystallization process that you have presented? Jochen also partially answered that question, said yes. One of our own alumni, Jill Banfield.
Okay.
I want to elaborate on that.
Yeah, maybe Jochen should answer that question. And it also depends on in which way do you want to model this. I mean, structurally or chemically, or yeah, I mean, physically it has been modeled, and it doesn't actually have to be modeled because you can measure it. Yeah, but the chemistry is the part that would be most interesting to us, I think, and that has not been modeled yet.
Can you hear me here?
Hoping to get to that.
More questions than that? You want to go?
That was a lovely talk, Dorrit.
Well, thank you, Penny.
Do you think that the sulfide in your polycrystalline aggregate is required to trap the fluid to make the diamond? Or?
Well, I mean, given it's a redox reaction, I mean, the fluids are most often, I think that we know, for the diamond fluids, most often they are carbonate. So it's, and I call them fluid because they're above the critical point. So they're a supercritical fluid. So they could be melt or fluid, but it's just at a point where you can't tell anymore if it's a melt or fluid. But most of them are carbonatic, so they're quite oxidized. There are some that are more methane bearing, but they're rare. So there are also people arguing for a pH being important in precipitating diamond, rather than redox reactions, but it seems to me that redox would be the obvious thing. So it doesn't have to be sulfide, it could be something else that triggers a redox reaction, but there is a lot of sulfide in aggregates and being subducted. So that's one obvious candidate.
I guess I was wondering too, I agree with that answer. I guess I was wondering too whether you think sulfide is pre-existing or whether it's precipitating the fluid to then.
Yeah, no, that one is clearly pre-existing, and
that's could it precipitate from that fluid and be pre-existing and then.
Well, I think that speaks to the solubility of sulfide in carbonatic fluids, and I think that's quite limited. I think what we know about the mobility of sulfide-based fluids and melts, it's quite restricted. They don't, the data we have, so as a community, in the mantle, sulfides do not migrate far. They're pretty local because they're quite reactive. And there's also, I think you would probably know more than me about this, about how the surface tension influences the mobility. And I think sulfides people think sulfides are not so mobile. So, and how to dissolve sulfides in carbonatic melt, that would be quite difficult because that's immiscible at that stage largely, at that P&T.
Thank you.
So given that redox is so important in diamond formation, then why has diamond formation been so consistent throughout Earth's history that the oxidation state of mantles increased a lot since the Archean?
Yeah, good question. It's a matter of scale, I would say. You've got, if you think about the mantle as such, you know, that's always a nice lens to think of homogeneous planetary style things, but subduction is quite local. Heterogeneity in the mantle can be quite local, and this is where you get the diamonds. Also, diamond is not distributed homogeneously throughout the mantle.
So if diamond formation is linked to subduction, what about Was the diamond formation before subduction was the thing?
Yeah, actually, probably not. I think that the ages we have on the diamond inclusions, what do you say there are no ages that are older than 3.3 billion years. And so, and that might be a circular argument, but the community is using this to argue this is probably the time where the Wilson cycle type of geodynamics started.
Well, I think on that, the old kimberlites as well, 2.8 about Kenyaki as well.
Yeah, but way younger. I mean, kimberlites are 2.5.
I think that also relates to the oxidation, increased oxidation of Mantle and the volatile concentration of Mantle.
Yeah, yeah. There's also the theory that you're actually collecting, outgassing carbonates or carbon in some form at the base of the subcratonic lithosphere, because that's just where it accumulates, and then you get an event that is either rifting of the craton or a plume activity that heats that up and creates, remobilizes it and creates the kimberlite. There's that view as well. So.
Right. Well, look, it's we are in person again, so it actually works to do some applause. So, why don't we do that? Thank you again. So, the in-person seminar next week, then students, once again, there will be an opportunity for some lunch with the speaker before the seminar. Okay, thank you very much.
Thank you.
Thank you everyone for coming.
Thanks very much. Thank you, online people. It still works.